In this tutorial we're looking at section 5.4 on scalar product and applications. So we can actually multiply vectors together, and there's two different ways that we can do that. So we can do that using the scalar or dot product, okay, and our answer will always be a scalar, or we can actually multiply them through the vector product, which will mean that we get an answer that will always be a vector. So our scalar product, okay, is a dot b, which is the way we read it, equals the magnitude of A times the magnitude of B times cos of the angle between them. So we read it as A dot B, where theta is the angle between the two vectors. And note the angle in between the vectors must be between the tails of the two vectors. So we're saying we've got one vector here, another vector there. Theta is the angle between the tails. Okay, so it's A dot B, or our scalar product. Okay, so properties of the scalar product. The scalar product always gives a number as a result, and it can be positive or negative. Okay, if A dot B is greater than 0, okay, if cos of theta is greater than 0. So that means that our angle between them is between 0 and pi on 2. And A dot B will be less than 0 if cos of theta is less than 0. Okay, that means that our angle is between pi on 2 and pi. And A dot B will be 0 if cos of theta equals 0, so that's when we're at pi on 2. A dot B is the same as B dot A. Okay, A dot A is equal to the magnitude of A squared, and A dot lambda B equals lambda A dot B, or lambda times A dot B. So basically we can have a constant anywhere in there and it doesn't make any real difference. Okay, and so just with this bit up here, this means that vectors are perpendicular. So if we have our angle of pi on 2, that's 90 degrees. Okay, so it means that A and B are perpendicular. So that's going to be a rule that we use. Okay, and we're going to use that as a test of perpendicularity, which I may or may not have just made up a word there. Okay, so often we'll want to see if two vectors are perpendicular, so we'll do the dot product. If it equals 0, bingo, they're perpendicular. Okay, keep moving on. Okay, we can look at it in terms of component forms. Okay, so we can say that I, j and k, remember they're our unit vectors. So the magnitude of I is 1, the magnitude of j is 1, and the magnitude of k is 1. That means that I dot I is 1, j dot j is 1, and k dot k is 1. So I, j and k are all perpendicular to each other. So that means that I dot j and j dot I are equal to 0, or I dot k or k dot I is equal to 0, or j dot k or k dot j are all equal to 0, since they're perpendicular to each other. Okay. In general, if we have vector A being x1i plus y1j plus z1k, and vector B being x2i, y2j and z2k, then the dot product of these two vectors is simply x1 times x2 plus y1 times y2 plus z1 times z2. Okay, this is when we're in our component form. Okay, so we'll have a look at this worked example. Okay, so we're given this setup here. So we've got vector A, which has the magnitude of 6. Vector B has the magnitude of 4 root 3, and the angle between them is 150 degrees. Okay, and we're going to find A dot B. So we know the magnitude of A is equal to 6, and the magnitude of B is equal to 4 root 3. Okay, and we know theta is 150 degrees. Well, then we need to say, well, A dot B is equal to the magnitude of A times the magnitude of B times cos of the angle between them. So say, well, our magnitude of A is 6 times our magnitude of B, which is our 4 root 3, times cos of 150. Okay, we'd say then that this is going to be equal to 24 root 3 times cos of 150, okay, is negative root 3 on 2, okay, which means that A dot B, I'll come up here, A dot B is equal to minus 36 when we expand that out. Okay, we'll keep moving on. Got a couple of other worked examples to have a look at. So this is a worked example of 13. So if A equals 2i plus 3j take 5k and B equals 4i take 5j take 2k, find A dot B. Well, for this, remember we were just saying a minute ago that when we're in our component form, okay, then a dot b is simply x1 times x2 plus y1 times y2 plus z1 times z2. So we can simply say that we have 2 times 4 plus 3 times minus 5 plus minus 5 times 2, which is going to be 8, times minus 2, which will be 8 take 15 plus 10, which is going to equal 3. So a dot b equals 3. Okay, worked example 14. If a equals 3i take 2j take 4k and b equals 2i take 5j plus zk and a and b are perpendicular, find the value of z. Okay, so what we're going to do is we're going to start off with doing our dot product. Okay, and just as we did up here, it's our x's times our x's, our y times our y, and our z's times our z's. So we've got 3 times. Sorry, just give me a second. I'm looking at the wrong one. So we've got 3 times 2, okay, plus minus 2 times minus 5 plus minus 4 times z. Okay, so when we do that, we've got 6 plus 10 take 4z. So we've got 16 take 4z. Okay, since a and b are perpendicular, we know that a dot b is going to equal 0. So we can then say, well, 0 equals 16 take 4z. So minus 16 equals minus 4z. So z equals 4. Okay, so as I said before, we can use the dot product, particularly when things are perpendicular, to solve different problems like we've done here. So we'll keep moving on. There's a fair bit in this tutorial that we need to get through. Okay, angle between two vectors. Okay, the formula a dot b equals magnitude a times magnitude b cos of theta can be rearranged for theta. So when you say that theta equals inverse cos of a dot b on magnitude of a times magnitude of b. So we're going to work the example for this. This is worked example 15. So if a equals I take 2j plus 3k and b equals 2i take 3j take 4k, find the angle between a and b. So essentially we're just going to be using this formula. Okay, but you can see there's various different things that we need to do. So to start off with, we're going to need to find a dot b. Okay, now because we're in component form, okay, we can again do what we've been doing. So we can say 1 times 2 plus minus 2 times minus 3 plus 3 times minus 4, okay, which is 2 plus 6 take 12, which gives us minus 4. Okay, so we know that. Now we need to look at the magnitude of A and the magnitude of B. So the magnitude of A, remember we do our three-dimensional pi tag, so it's coefficients of E squared, so 1 squared plus minus 2 squared plus 3 squared, which equals the square root of 1 plus 4 plus 9, which equals the square root of 14. And we say the magnitude of B, we do the same thing. We've got the square root of 2 squared plus minus 3 squared plus minus 4 squared, which gives us the square root of 4 plus 9 plus 16, which is the square root of 29. Okay, so we're getting there. Okay, so we know that, and now basically we've got everything we need to build up our equation. So we say, well, theta is going to equal the inverse cos of a dot b, which is minus 4, over magnitude of a, which is root 14, times magnitude of b, which is root 29. Okay, So we're getting there now. Okay, so when we do this, we just use our calculator at this point. Okay, but we know that our angle is going to be negative. Okay, so the angle between our two vectors will be obtuse, or between 90 and 180. So we find that we get theta is equal to 101.45 degrees. So we get to something like this. Okay, it's clearly not going to be one of our exact values, so we'll go and plug it into our calculator. Okay, so we'll keep moving on. So finding magnitude of vectors. So the magnitude and the sum or difference of vectors can be found using these. So a dot a equals the magnitude of a squared, and a dot b is the same as b dot a. So we're saying for worked example 16, okay, if magnitude of a equals 3, and the magnitude of b equals 5, and the magnitude of a dot b is minus 4, find the magnitude of a plus b. Okay, so what we want to be doing, okay, is saying the magnitude, okay, of a vector squared is attained by finding the dot product of the vector with itself. So what we can say is, basically, we're going to undo this. Okay, so we're going to say then that we're going to actually look for the magnitude of a plus b squared. Well, that's going to be equal to a plus b dot a plus b. Okay, so when we do that, we need to expand our brackets, and what we get is, what we can do is go, well, we can say a dot a plus a dot b, okay, plus b dot a plus b dot b. Okay, so then we can simplify this a little bit, because we know a dot a, well, that's going to be the magnitude of a squared, okay, plus a dot b is the same as b dot a, so we can say we've got two lots of a dot b, plus b dot b, same idea, it's going to be the magnitude of b squared. Okay, now that means that we get the magnitude of a plus b squared equals, okay, well, the magnitude of a is 3, so the magnitude of a squared will be 3 squared, okay, plus 2 times a dot b. Okay, we've got a dot b. Let me just double check. Oh yeah, we know where our 2 times our negative 4, yeah, sorry, we've got our magnitude of a dot b is negative 4, and we've got two lots of it. Sorry, so 2 times negative 4, plus the magnitude of b squared is 5 squared. So sorry about that. So 2 times a dot b, well, we know the magnitude of a dot b is negative 4. So that's why we put in our negative 4 there. Okay, so that means that we get 9 squared, sorry, just 9, what was I saying, 9 squared, 9 take 8 plus 25, which means we're at 26, which means, and that's, don't forget that's a plus b squared. Okay, that means that the magnitude of a plus the magnitude of b is going to equal square root of 26. Okay, but unfortunately we're not done, we've still got a bit more to do. Okay, so projections. So the scalar resolute, sorry. The projection of A, which is OA, onto vector B, which is OB, is a process of drawing a line perpendicular to OB at C as shown. So what we do is, the way I always like to think of it, is if I put a light up here, up the top, okay, it's going to be the shadow that this vector casts on this vector. Okay. So the projection is defined as the distance OC and is called the scalar resolute of A onto B, or the scalar resolute of A parallel to B. Basically what you're really doing is we're really saying, let's break this vector, okay, into its components, where one is parallel to this vector and the other one's going to be at right angles. So we're going to find the distance O to C, okay, by A dot B over the magnitude of B. Hey, our parallel vector resolute. So the vector resolute of A onto B is the vector OC. Okay, so it's actually our vector, not just our distance. Okay, as shown. So OC is going to equal A dot B hat times B hat. Remember, B hat is the unit vector in the B direction. So vector resolutes are also called the component of vector A onto vector B or parallel to vector B. Okay, so just a bit of terminology there. But basically we're saying now we're looking at this vector here. Well, the component that's in this direction. Okay, and then we have our perpendicular vector resolute, which is going to be this one in the blue. Okay, and so we say that's vector CA, and we find CA by A minus A dot B hat times B hat. Okay, remember again, they're our unit vectors. Okay, so up to our last worked example. Okay, so we've got given vectors u equals 3i take j plus 2k and v equals 2i take 3j take k. Find, and the first one is the scalar resolute of u in direction v. So we want scalar resolute of u in the direction of v. Okay, so to do that, okay, we know that v is our 2i take 3j take k. So the magnitude of v equals the square root of 2 squared plus minus 3 squared plus minus 1 squared. Okay, which is going to be the square root of 4 plus 9 plus 1, which equals the square root of 14. Okay, so to get v hat then, okay, then it's simply 1 over the magnitude of v, which is square root of 14, okay, times by our v, which is our 2i take 3j take k. Okay, if you can't remember, you'll have to have a look back at your previous work on unit vectors. Okay, now we need to look at u dot v. Okay, so u dot v, okay, remember it's just going to be this times that plus that times that plus that times that. So we're going to get 3 times 2 is 6, okay, plus minus 1 times minus 3 is going to be positive 3, and then 2 times minus 1 is going to be take 2. So u dot v is going to equal 7. Okay, so our scalar resolute, okay, of u in the direction of v is given by u dot v hat, okay, which equals u dot v on the magnitude of v. So that's going to equal our u dot v is 7 over our magnitude of v is going to be our up here, our root 14. Okay, and so we're going to rationalise the denominator. So we're going to times it by root 14 on root 14, which means we're going to get our root 14 on 2. Okay, so that's part A. Part B, okay, we want the vector resolute of u in direction v. So a vector resolute, just change colours on it. Our vector resolute okay, remember we find that by u dot v hat times v hat. Okay, so we know that our u dot v hat, okay, is our what we just found. Okay, our u dot v hat, so that's our root 14 on 2. Okay, and we've got to times that by v hat, which we have over here, we found that earlier, times by 1 on root 14 times 2i take 3j take k. Okay, our root 14s are going to cancel out. Okay, they're going to cancel out, so we're going to be left with a half outside of 2i take 3j take k. And that's all we need to do. You could expand out your brackets if you like, but it's not going to help you that much. So we can actually say we're done there with our vector resolute. And the last part is a vector resolute of u perpendicular to v. So we find that by, sorry, I'll change colours again. We find that by our u minus our u dot v hat times v hat. Okay, so our u, so that's going to equal our u, which is 3i take j plus 2k. Take away this part, well, we just found our vector resolute, so we've got to take away our half of our 2i take 3j take k. Okay. So when we do that, okay, we can run through and do our different parts. So just give me a second. Okay, so what we can do, okay, they do a little bit funny here, but what they do is they go, well, we'll take half out as a common factor. Okay, but that means that we've got to times this one by 2. Okay, and then this one will just be what it was, which is 2i take 3j take k. Okay, so you can keep going here, and well, we can multiply out this and give us 6i take 2j plus 4k minus 2i plus 3, sorry, that should be in a j, 3j, a plus k, which means we get a half outside of 6i take 2i is 4i minus 2j plus 3j will be 1j, and 4k plus k will give us 5k. Okay, so I did a little bit of a funny step in there. Okay, I probably wouldn't have done it that way, but that's fine. Okay, and so we get our answer. And now that is the end of this section. So I know there was a lot in here. You may need to re-watch the video to get you through the questions.